So welcome everyone to today's session of the Seminario FLOTANTE de Lógica. It is a great pleasure for me to introduce Alex Kruckman from Wesleyan University, and who will be talking about a continuous zero-one law for finite metric spaces. So thank you, Alex, for accepting the invitation, and the screen is all yours.
Great, thanks a lot for the invitation. It's nice to be in Bogota virtually, hopefully one in person. So yeah, I'm going to talk about a zero-one law in the context of continuous logic. And this is all joint work with Isaac Goldbring and Brad Hart, although I want to make it clear that actually this is mostly Isaac and Brad's work. I joined the project quite late. They were generous enough to add me as a co-author after I pestered them enough with corrections on drafts of their paper. But I think it's quite interesting. I wanted to report on it to the Bogota community. Okay, so I'm going to talk about classical zero-one laws first, just as a refresher, and then talk about what goes into generalizing the notion of zero-one law to metric structures and continuous logic. And we'll focus on metrics, the simplest possible metric structures, which are just pure metric spaces. And we'll look at the actual zero-one law theorem for finite metric spaces and characterize its almost sure theory. And then at the end, I'll talk a little bit about pseudo-finiteness and pseudo-finite.
Correcto. Creo que debió interferir.
And in particular, the example of the Eurozone sphere. And the question, which is an open question, of whether the Eurozone sphere is pseudo-finite in continuous logic. Okay, that's the plan. So for classical zero-one laws, the setting is we fix some finite language, L, and some class of finite L structures. Typically, these will be closed under isomorphism and probably substructure. And we look at Kn, which is the class of structures from K, which has domain the set of natural numbers from 1 through n. So these are not just structures of size n up to isomorphism, they're actually labeled structures of size n. That is, the elements of their domain are labeled by the natural numbers 1 through n. So because the language is finite, there's only finitely many structures in Kn. And we'll take mu n to be the uniform measure, the counting measure on Kn. Okay. So we say that this class of structures has a first order zero-one law for the uniform measures. If whenever I pick a sentence in my language and I count what percentage of the structures in Kn satisfy the sentence according to the counting measure, and I take the limit as the size goes to infinity, then these percentages, these probabilities limit to 0 or 1. So in other words, to say that a sentence has probability 1, here limiting probability 1, is to say that if I pick a large structure from my class at random, it's almost surely going to satisfy the sentence phi. Okay. Now I put here for the uniform measures, it's reasonable to consider other kinds of measures on the Kn's or other spaces of finite structures. But for the purposes of this talk, we'll stick with the most common case, which is where we look at the uniform measures on the Kn's. Okay, and then if you have a zero-one law, then you can collect up all the sentences with limiting probability 1 into a complete theory. Complete because every sentence has limiting probability 0 or 1, so every sentence or its negation will have limiting probability 1. Okay, we get a first order theory, which note will have only infinite models, right? Because we're letting the size of the structures go to infinity. So the sentence which says I have at least n elements in my structure will start holding 100% of the time once your structure has size greater than that n, and so that'll be in the theory. So how do you prove a zero-one law? Seems kind of tricky because you have to sort of quantify over all first order sentences. Well, typically the recipe is like this. You write down some axioms that you think are going to hold almost surely. Then you show the axioms hold almost surely. That involves some counting, some combinatorics. And then you show that those axioms axiomatize a complete theory T, and that's the logic side of things. And voila, you have a zero-one law with almost sure theory T, because if some sentence follows from the axioms logically, and the axioms hold almost surely in arbitrarily in large enough finite structures, then the logical consequence of them will also hold almost surely in large enough finite structures. Okay. So this recipe just allows us to focus on axioms of a particular simple form, and if they axiomatize a complete theory and hold almost surely, then we get a zero-one law. So I want to start with a really very trivial example, which is where we take the language to be empty. So the class K is just the class of finite sets. Right? We only have the primitive symbol for equality in the language. Well, what are the sentences that are going to hold almost surely? As I mentioned a moment ago, the sentence which says there are at least n elements in the domain will definitely hold almost surely. And if you drop all those sentences into a theory, you find that this is a complete theory, right? Because there's no other symbols in the language. The theory is complete because all infinite sets are elementarily equivalent. You could also say this follows from the fact that this theory is countably categorical, right? And has no finite models. So that's the simplest possible case of the 0-1 law. If there's no structure in the language, these sentences saying structures are large hold for large enough structures 100% of the time and axiomatize a complete theory. So we have this 0-1 law for finite sets with almost sure theory, the theory of infinite sets. Of course, things get more complicated when we add some symbols into the language. So the most famous classical case of a 0-1 law is the 0-1 law for finite graphs. So now my language is just R. It's a binary relation. We think of a finite graph as an L structure. So here's some notation. If I have a finite graph in Kn, so its elements of its domain are labeled 1 through n, I'm going to let conf A for configuration be the formula which expresses exactly what the graph looks like on variables where there's one variable for each element of the domain, right? So this is just the conjunction of the atomic diagram of the structure. It says that there's an edge between xi and xj just when there is an edge in the graph between vertices I and j, and there's not an edge between xi and xj just when there's not an edge in the graph between I and j. Okay, and now if I have a structure A, a graph in Kn, and a one-point extension of it, that is a graph with one extra element, I can write down the extension axiom, phi for A sitting inside B. And this says, whenever I have a copy of A, an isomorphic copy of A, that is a tuple satisfying the conf A formula, then there is some element in the structure where when I add it to that tuple X, I get a copy of B, that is a tuple X bar Y satisfying the configuration of B formula. So these are going to be our axioms. I should say here that our theory T is these extension axioms together with the axioms of graphs. So we have to say that R is symmetric and irreflexive. Forgot to mention this. But a counting argument will show that these extension axioms hold almost surely in large enough finite graphs. And they axiomatize countable categorical theory with no finite models. So they axiomatize a complete theory. To prove the countable categoricity, you do a back and forth argument. Right? If you have two infinite graphs, countable infinite graphs, which both satisfy all the extension axioms, you can use the extension axioms to start building an isomorphism between these graphs back and forth. And we have a name for the unique countable model of this theory. It's the random graph. And in this case, it happens to be the Froissart limit of the class of finite graphs. Right? The class of finite graphs is a Froissart class. It's closed under substructure and has the joint embedding property and the amalgamation property. This allows us to build a universal homogeneous countable graph, and that universal homogeneous countable graph is exactly the countable model of our theory T. Okay, I think that this is all originally due to Fagin and possibly independently some other people, but Fagin is the usual attribution. I think at least for the connection between the 0-1 law and the random graph. Correct me if I have that wrong, please.
Well, I think that some Russians did it year before Ron.
Okay, yeah, that's what I was thinking. Did they have the connection to the random graph also? I haven't seen their paper, because it's.
I don't know. I mean, the other key point here is that Harari and Blas are the ones who actually laid it out this way with the extension axioms.
Okay, so I should really be crediting more people than just Fagin. I wasn't totally sure about it, and that's really why I left the attribution off the slide, actually. So, apologies to all the people that I didn't, whose names I didn't put on this slide. Okay. Thanks, John.
Yeah.
Okay, third example. Let's modify the previous example and think about not all finite graphs, but just the finite triangle-free graphs. And here we again have a Froissart class. The Froissart limit is usually called the Henson graph or the generic triangle-free graph. But this time, the Froissart limit is not a model for the almost sure theory. So we have a Frisé limit and we have a 0-1 law, but the Frisé limit is not a model for the almost sure theory for the 0-1 law. And the reason why not is this asymptotic result due to Erdős-Kleitman and Rothschild that says essentially almost all finite triangle free graphs are bipartite. Okay. So a bipartite graph doesn't just omit a triangle, it also omits all 5 cycles and 7 cycles and all odd length cycles. And if you look at the axiom saying there's no pentagon in the graph, this axiom will hold with limiting probability 1 in the triangle free graphs. On the other hand, the Frisé limit, the Henson graph, all finite triangle free graphs embed into it. In particular, a 5 cycle embeds into it. And so it satisfies the axiom saying there is a pentagon, whereas the almost sure theory says that there are no pentagons. Okay. But building on the Erdős-Kleitman and Rothschild result, Koletis, Fromel, and Rothschild, and independently Henson, Henson just did the case of the triangle free graph, and Koletis, Fromel, and Rothschild looked at Kn free graphs emitting a clique of size n for all n. But they proved that basically this bipartite restriction is the only restriction that forces the triangle free graphs to differ from some Frisé limit in the following precise sense. The triangle free graphs have a 0-1 law, and the almost sure theory is the generic theory of bipartite graphs. Okay, you have to be a bit careful about what you mean by the generic theory of bipartite graphs, because in the graph language, bipartite graphs are not a Frisé class. But there's a natural way of axiomatizing a generic theory of bipartite graphs, again with extension axioms, like in the previous slide. So this almost sure theory is an also not categorical theory, can be axiomatized by extension axioms for bipartite graphs, and those extension axioms hold almost surely in the limit on all triangle free graphs. And so they axiomatize.
Can I ask a question? Wait a sec. The first theorem of Erdős, is there a clear way of saying that almost surely the graphs are bipartite?
Yeah. So if you take Kn to be the set of all triangle free graphs with domain 1 through n, and then you look at what percentage of Kn are bipartite graphs, and you take the limit as n goes to infinity, that percentage will limit to 1.
No, I know, but the point is, can you count it explicitly? Like the way you count which ones are bipartite. There's an actual formula that you can tell, look, it's, I don't know, this proportion of all graphs or so on. Like, I know it's saying that eventually it's true, but do you know what the proportion is, or
you're asking
like what the formula is?
Asymptotics. Some bound on how fast the probability goes to 1. Is that what you're asking for?
Yeah, like an explicit formula. Is it clear?
I believe that there are asymptotics in the Erdős-Kleitman Rothschild paper. I don't remember what they are off the top of my head, but certainly the way that they proved this was to bound, give some bound for how fast this thing goes to 1. Yeah.
Thanks.
Okay. So that was my quick crash course on classical 0-1 laws. Now I want to give an even quicker refresher on continuous logic. I think there was a talk last week by Kiesler in the seminar on continuous logic, or maybe the week before. So that'll excuse me going extremely quickly through the main idea. Okay, so what is continuous logic? It's a generalization of first order logic to metric structures, that is, expansions of metric spaces. So ordinary first order structures are sets with extra structure, metric structures are metric spaces with extra structure. Okay. And so here's the basic translation for how this generalization goes. We replace the truth values in classical logic, true and false, with the unit interval. So we have these generalized truth values between 0 and 1. And we're going to think of 0 as being true and 1 as being false or far from true. And we replace the equality symbol, primitive equality symbol in classical logic, with the metric symbol. So rather than just asking whether two elements are equal or not, you can ask what's their distance. And this explains why we think of 0 as being the analog of true, because to say that two elements are equal in a metric space is to say they have distance 0, right? So truth of equality corresponds to value 0 for the metric. We replace relation symbols in classical logic with functions from n tuples to the truth values, which are uniformly continuous. We replace Boolean connectives with arbitrary continuous functions from some power of the unit interval to itself, right? You can think of the Boolean connectives in classical logic as generating all Boolean functions from the, n tuples of truth values to truth values. And so a natural generalization of this is to take the kth power of the set of truth values, that is the unit interval, and consider functions. Well, now we want to restrict to continuous functions so that they're nice, back to the set of truth values. And then the generalization of quantifiers is going to be sup and inf. And again, just to give some motivation for this, what does the universal quantifier say when we look at a formula in classical logic? It lets us scan over the whole structure and say, no matter what element we pick, if we plug it into the formula, we'll get true. Okay, what would it mean for a supremum over values of x to be true? Well, true, remember, in our continuous setting is value 0. When is a supremum 0? Well, it's when all values of x give you value 0. Okay. The other direction is kind of interesting because the existential quantifier lets you range over the structure, and it returns true just when there's some element where when you plug it into the formula you get true. Well, on the other side, we sort of get an approximate truth, right? Because if you think of plugging in various values for y and taking the infimum is going to be 0, that is, the formula is true, just when you can get arbitrarily close to 0. So for any epsilon, there's a value of y which will make the truth value of the formula less than epsilon. Okay. So often when we, in theorems about continuous logic, there will be generalizations of theorems in first order logic, but you'll have to include some sort of epsilon fudging, saying that something happens as close to true as you like. Okay. We'll see some examples of that in a moment.
Sorry, a quick question. Is there a quick explanation of why we want uniform continuity instead of just continuity for relation symbols?
So there's various formulations of continuous logic, and I think there are some formulations that weaken that requirement. I'm probably not. I don't have a quick answer for you as to what exactly uniform continuity buys us. Maybe somebody else who's here would be better.
Yes, you want to be that if you take an ultra product and you have the same bound, that the ultra product will keep the bound and will be again continuous. If they were only continuous as opposed to uniformly continuous, you wouldn't be closed on their ultra products.
That makes sense. Thank you.
Basic trick.
Appreciate it.
Thank you.
Okay, so when I first looked at the definition of continuous logic, right, I think that the scariest thing for me from this generalization was the idea of considering all continuous functions from the power of the unit interval to the unit interval as Boolean connectives. And for the purposes of this talk, we can get away with a very small set. We'll really only use, I think, max, min, constant functions, and this truncated subtraction operation. Right? So in general, of course, you can restrict from all continuous functions to just some set using which you can arbitrarily closely approximate an arbitrary continuous function. In our case, we'll just use a couple of examples of these Boolean connectives. This truncated subtraction is important, right? We take x and subtract y, and we'd like the value to again land in the unit interval, not be a negative number. So you just subtract y from x and cut off at 0. And it's important, we'll use this operation on x and y a lot. If you think about it, what is it saying? Well, it's saying that the truth value of x is less than or equal to the truth value of y. That is, you get the value 0 from x minus dot y, just in case y is greater than or equal to x. Okay. So again, in this talk, we're just focusing on metric structures, metric spaces, which are the simplest example of metric structures. We're working in the empty language. So the only atomic formula is the metric. And this is the analog of our first example of a 0-1 law in the classical setting, where we just considered sets with no extra structure. So a metric L structure is just a metric space valued in 0-1. Whenever I say a metric space is valued in some set, I mean whenever you pick 2 points, let's say distinct points, their distance lies in that set. So given a continuous L sentence, phi, and a metric space M, there's a natural semantics. You get a truth value for that phi in the metric space M, and it's a real number phi super M, which lives in the unit interval. And we say that M satisfies the sentence phi, or respectively a theory T, if the truth value is 0, respectively the truth value of every sentence in the theory is 0. So I mentioned earlier that there's now a game of taking results of classical model theory and generalizing them to continuous logic. The first one you might hope to see is a compactness theorem. And here's a compactness theorem which is actually a little bit stronger than the one you might naively expect, because it has this sort of approximate character. So if I have a continuous theory, I can change it by saying, well, I don't need the sentences to hold exactly, but I need to hold them. I need to have them hold with truth value less than epsilon for all epsilon. Okay. This T plus has the same models as T, right? Because if I take a metric structure to say that the truth value of phi in that structure is less than epsilon for every epsilon is the same as to say that it has truth value 0 in the structure. But it's a little bit easier to satisfy finite subsets of this set of this theory T plus, right? If I take finitely many sentences in this T plus theory, this just picks finitely many sentences of the original structure and asks that they hold approximately, that is closer than epsilon for sense. Okay. And then the compactness theorem, this approximate compactness theorem, says that the continuous theory is satisfiable if and only if this associated theory T plus is finally satisfiable. And an idea for how you might prove this with maybe with an ultra product proof is just to note that well, if you take models which approximately satisfy finite fragments of the theory close enough, and then take their ultra product as epsilon goes to 0, you'll end up getting actual satisfaction, truth value 0 in the ultra product. Okay. So, given that background, we want to think about what it would mean to formulate a continuous 0-1 law for metric spaces. There's two issues that crop up. The first one is, what is the analog of the uniform measure? You know, in the classical setting, we fixed a finite language. That meant there were only finitely many L structures with domain 1 through n, period, so we could just count them. But of course, there's uncountably many metric spaces, even of size 2, right? Because the 2 points could have any distance in the unit interval. So the way we're going to solve this problem is to replace the counting measure with the natural kind of uniform measure on a continuum, which is the appropriate sort of power of the Lebesgue measure, restricted power of the Lebesgue measure. So for a metric space X, I'm gonna encode a finite metric space with domain n by just a tuple of values, namely the distances between all the points. Right? So how many distances does it take to specify a metric space with n labeled elements in its domain? Well, for each pair of distinct points in n choose 2, we just need to specify the distance between those points. So we code this metric space X with a tuple in the n choose 2 power of the unit interval. Okay, and now not every choice of distances actually gives you a metric space, because some of them will violate the triangle inequality. So Mn is some subset of this power of the unit interval, which is the set of all tuples which actually encode metric spaces. Okay. Great. Well, on the power of the unit interval, we have a natural measure, the product measure of the uniform measure on 0, 1. And we can just normalize it to this closed subset of the power of the unit interval Mn. Right? So I just, to find the uniform measure of a set of finite metric spaces, I just divide the Lebesgue measure of that set by the Lebesgue measure of the set of all metric spaces of that size. Okay, this gives us a natural kind of interpretation of choosing a metric space uniformly at random. Okay, the second issue that crops up is sentences can take arbitrary truth values in the unit interval, and we have this sort of flavor of approximation happening in continuous logic. What kind of convergence do we actually expect? And I'll answer this by just telling you the statement of the theorem. So for any sentence in the continuous language of metric spaces and any positive epsilon, there's some truth value in the unit interval, so that if you look at the set of metric spaces of size n, which satisfy that sentence whose truth for the truth value of that sentence is within epsilon of that target at like actual truth value, the measure of this set limits to 1 as n goes to infinity. So maybe it'd be more appropriate to call this a convergence law than a 0-1 law, right? I'm specifying some target truth value for every sentence, and I'm saying that that with probability 1 in the limit, a large finite metric space approximately satisfies that sentence having that particular truth value, where approximately means within this fixed epsilon. Okay. So in other words, we don't expect the sentences to take on their target truth values exactly in any actual finite metric spaces, just close enough in almost all finite metric spaces. Okay, so what I'd like to do is outline the main steps of the proof. And we're going to follow the recipe that I outlined earlier for classical 0-1 laws. We'll axiomatize a complete metric theory, continuous theory, which gives these target truth values to the sentences in every model of the theory. And to axiomatize that almost sure theory, we'll use extension axioms like we did for random graphs, but modulo a major restriction, which is this fact. Almost all finite metric spaces are approximately valued in the upper half of the unit interval. Okay. In other words, for almost all finite metric spaces, if you pick 2 distinct points, they will have distance greater than or equal to 1/2, almost. Okay. So this fact comes from a recent unpublished work of Kozma, Meyerowitz, Pellet, and Semeti. And this is a less precise version of their theorem. They actually give some asymptotics for this sequence delta n. But the crucial thing that we need is that there's a decreasing sequence of numbers that are greater than 0 but less than half, tending to 0, so that if we look at the set of all finite metric spaces, where all of the distances are almost greater than or equal to 1/2 up to this little delta n error, so they might be a titch below 1/2, then the limit as n goes to infinity of the measure of these metric spaces is 1. So you have the deltas in advance, you take the measure of the metric space of size n, whose distances are greater than or equal to 1/2 minus delta, a little bit below 1/2, and you take the limit as n goes to infinity, you get 1. Okay. So let me point out how to think about this a little bit more easily. We might hope that actually almost all metric spaces, finite metric spaces, have values in the interval from 1/2 to 1 without this fudge factor, without this little delta n. There's a really special thing about that set Cn, which is that every choice of distances between 1/2 and 1 actually defines a metric space, because violations of the triangle inequality are impossible, right? If you have a triangle, 3 points, and you specify the distances between them arbitrarily in the interval from 1/2 to 1, well, the sum of any 2 numbers between 1/2 and 1 is greater than or equal to 1, right? So you can't violate the triangle inequality no matter how you pick the distances. Okay, so there's a natural question. Well, is it actually true that almost all finite metric spaces have values strictly in the interval between 1/2 and 1? This appears to be unknown. The theorem of Kozma, Meyerowitz, Pellet, and Semeti requires this slight fudge factor, right? So it's possible, even though the delta n's are approaching 0, so we're getting closer and closer to requiring all distances at least 1/2. It's possible that the volume of metric spaces who have some distance that's just a hair below 1/2 actually has positive measure in the limit as n goes to infinity. Okay, somehow this seems unlikely. It would be really nice to actually have the limiting probabilities, limiting measures of these Cn's being 1, but it doesn't follow from what they did, as far as we can tell. Okay. So we want to use this restriction to write down some extension axioms to axiomatize the almost sure theory and establish the 0-1 law. Okay, so step 1 of the recipe is write down some axioms. So first of all, let's write down the sentence which says all distances are greater than or equal to 1/2. So again, I'll try to talk through what these continuous sentences mean for those of you who are not used to reading sentences in continuous logic. Remember, the soup is supposed to be the analog of the universal quantifier. So when would this sentence have truth value 0? Well, it's for all x's that you pick, it's true that for all y's you pick. So then the minimum, so either the distance between x and y is 0, that is x and y are equal, or if they're different, then this truncated subtraction is 0, that is the distance between x and y is greater than or equal to 1/2. So this fairly straightforwardly says this sentence has truth value 0 just when all the distances in the metric space are greater than or equal to 1/2. Now we want to write down extension axioms to axiomatize the theory modulo that previous phi greater than or equal to 1/2 sentence. So I'm going to let conf x, the configuration formula for a metric space X, denote this formula. Remember, the dij's are the actual distances in X, and we're going to say that that the max, we're going to look at the formula, which is the max of the differences between the distances we see between the vi's and vj's and the target distances dij. Again, this formula will have truth value 0 just when the distances between vi and vj are actually exactly equal to the distances vij in X. And then here's the analog of the extension axioms. If y is a 1-point extension of X, then we can write down the sentence psi x into y with error term epsilon. And this says that the supremum over v, so remember this is like for all v, of this minimum, okay, so the first term, epsilon minus conf x of v, that is 0 just when the configuration formula on v has value greater than or equal to epsilon. That is, right, so this term goes to 0 if the v's don't look close enough like x in the metric space we're looking at, right? So by taking the minimum here, we're restricting to just those v's which actually do look within epsilon of x. And then we take the inf of y, remember that's like an existential quantifier of the truncated subtraction of the configuration formula for y by epsilon. And this then says that v together with y looks very much like y within epsilon. So this is sort of like an approximate extension axiom. Stepping back, it says, whenever I take a tuple from my metric space, if it looks epsilon close to x, then I can find some extension which looks epsilon close to y by a new point w. Okay, any questions on this stuff? Does this all seem clear? Okay, so I'm going to let my almost sure theory be the theory axiomatized by my phi greater than or equal to 1/2 sentence, which says distances are at least 1/2, and then these extension axioms. Okay. So now we want to show that these axioms hold almost surely. And remember, the four-author theorem fact from the previous slide said it's not actually true that almost all metric spaces have distances exactly greater than or equal to 1/2, just close enough, right? So why should we expect this sentence phi greater than or equal to 1/2 to hold almost surely? Well, remember when we formulated the 0-1 law, we said not that the sentences actually have to hold exactly in almost all finite structures, but within some error bound epsilon. So if I fix up my error bound epsilon, then I can just go far enough out so that my delta n is smaller than epsilon. Remember, they decrease to 0. And then all of my almost all my finite metric spaces have all of their distances greater than or equal to 1/2 minus delta n. That is within epsilon of being all greater than or equal to 1/2. And so we actually get this limiting probability of satisfaction of this sentence within truth value epsilon being 1. Okay. So we'd like to show that the same is true for the extension axioms. And the idea here is that this would be a really easy computation if we actually restricted to the set Cn, which is the metric spaces with distances actually greater than or equal to 1/2. Why? Well, the measure localized to Cn is actually a product measure. Right? So we can think of picking a random metric space because there's no triangle inequality restrictions. We can think about picking a random metric space in Cn as actually independently, uniformly at random, deciding on all the distances between the pairs of points. And that sort of ability to think of picking a structure at random as uniformly assigning the relations at random independently is sort of what makes the argument in the case of the 0-1 law for random graphs go through. There's a probability counting argument which uses independence in a strong way. Okay, so if we just restricted to the Cn, we could use exactly the same kind of argument. But we're not restricting to Cn, we're restricting to Mn, the collection of all metric spaces of size n. And okay, we know that Dn, this collection of things of metric spaces where the distances are approximately greater than or equal to 1/2, has full measure in Mn. Okay. So the idea of the proof, and I'm going to spare you the estimates, but the Dn has measure 1 in Mn, and metric spaces in Dn are close enough to being in Cn that we can give approximately the same argument. Okay. So every metric space in Dn is within epsilon for if n is large enough of being in Cn, and so because our configuration axioms just ask for equality of distances up to epsilon, we can rely on the counting argument in Cn to give us the result for Dn as well. Okay, that's the idea of the argument. Of course, there's messy inequalities to deal with to make it go through, but that's the basic idea. Okay. And then step 3 was to show that this almost sure theory we wrote down is complete. Okay, for a continuous theory, being complete means that if you take any two models, x and y, then they're elementarily equivalent. What does it mean to be elementarily equivalent continuous logic? It means that every continuous sentence gets the same truth value in the two structures. So in the classical examples, we showed completeness for the almost sure theories using Aleph-Knot categoricity. You might hope to do the same thing here. The analog of Aleph-Knot categoricity for continuous logic is separable categoricity. So there's very few interesting actually countable metric structures. So instead, you ask for a structure with a countable dense set. But this almost sure theory is not separately categorical. So its models are actually kind of silly from the point of view of continuous logic, because any model is topologically discrete. Right? We're just looking at metric spaces with distances greater than or equal to 1/2. If you have two distinct points, their distance is greater than or equal to 1/2. So the ball of, say, radius 1/4 around any point contains just that point, right? So topologically, these models are just discrete spaces. So a separable model is really a countable model. And the theory is definitely not countably categorical, because a countable model can already have continuum many possible values of the metric. So there's continuum many countable models up to isomorphism. Okay, but really, the extension axioms would let us do a back and forth argument if we didn't require exact agreement of distances, but rather approximate agreement. And we can capture this with the use of Ehrenfurth-Bessay games for continuous logic. Okay. So on the next slide, I'm just going to write down here the definition of the Ehrenfurth-Bessay game, the approximate Ehrenfurth-Bessay game for continuous logic. Don't expect you necessarily to read it, but it's what you might expect. So the n-round game, Ehrenfurth-Bessay game between two metric spaces x and y, proceeds with the players alternately choosing elements from either structure. You play for n rounds, and then player 2 wins the game if the two structures of size n that you've selected from x and y are approximately isomorphic, meaning that their distances are within epsilon from another. Okay. And the fact is that the Ehrenfurth-Bessay games, the approximate Ehrenfurth-Bessay games, characterize elementary equivalence. X and y are elementarily equivalent if and only if player 2 can win the EF game of n rounds with possible error bound of epsilon for all natural numbers n and epsilon greater than 0. And our extension axioms exactly allow us to provide a winning strategy for player 2. If you think about what they say, they really say, given any finite metric spaces you've built up so far, if you choose a new point and see all the distances and how it's connected to the previous points, you can find another point in your second model y where the distances are within epsilon of the distances you see on the other side. Okay. So with all the ingredients in place, you can put it together to get a proof of the 0-1 law. For any continuous sentence, because the TAS is a complete theory, there's some unique real number in the unit interval such that every model of TAS gives truth value R to that sentence sigma. So that means that if you take the almost sure theory and throw in the sentence which says that sigma has truth value greater than epsilon from this sigma AS, that theory is not satisfiable. By this approximate version of the compactness theorem, the unsatisfiability, the inconsistency there would be witnessed by finitely many of the extension axioms, right? These psi, that should be a capital psi based on the notation I used before, epsilon I, xi going into yi. And it would be witnessed by a failure to even approximately satisfy with error-bound eta the extension axioms. So we would have that this set is unsatisfiable. Okay, but now we use our 0-1 law. Almost all sufficiently large finite metric spaces satisfy the all distances greater than or equal to 1/2 axiom with up to error-bound eta, and the conjunction of finitely many of the extension axioms with error-bound eta. So they have to also satisfy that the difference between the truth value of sigma and sigma AS is at most epsilon. And that's exactly a rephrasing of the limiting probability that we wanted to show. Okay. Really, this is a direct analogy for how you argue in the classical case with discrete structures. Okay, so having identified the almost sure theory, it's natural to ask what sort of classical model theoretic properties it has. It has quantifier elimination. It's the model completion, in fact, of this formula, the sentence which says all distances are greater than or equal to 1/2. This is somehow not surprising, right? It's taking that sentence that says all distances are greater than or equal to 1/2 and completing generically by adding in extension axioms. So it should be model complete. As I noted before, it has continuum many separable models up to isomorphism, no prime model. So it's not separably categorical, but it is sort of approximately separably categorical, right? Any two separable models have a back and forth system between them. And for stability theoretic properties, it's unstable, but it is simple if you rank 1, witnessed by the fact that forking is totally trivial in this theory. So there's no dependence between A and B over C unless A and B have an element in common that's not at C. And finally, it's pseudo-finite. Of course, it's the almost sure theory for a class of finite structures. It will be pseudo-finite, but it's worth maybe spending a minute, last couple slides here, to discuss pseudo-finiteness for continuous theories in general. So what does it mean for a theory to be pseudo-finite? Well, let's start by saying a structure is pseudo-finite if anytime a sentence is true of all finite structures, then it's true of that structure. Okay. That's a direct analog of one of the equivalent definitions of pseudo-finiteness for classical logic. And the natural equivalences that you might expect are true. This is due to Goldbring and Lopez, who wrote a paper on pseudo-finiteness for continuous logic. A structure is pseudo-finite if and only if it's elementarily equivalent to an alter product of finite structures, if and only if every sentence in its theory has a finite model approximately. Right? So this is the one wrinkle where approximation comes in the continuous setting. We don't say any sentence which has truth value 0 in M has truth value 0 in some finite structure, but rather has truth value less than epsilon for arbitrary positive epsilon in some finite structure. And then a complete theory is pseudo-finite if all of its models are. So we don't actually know very many examples of interesting pseudo-finite continuous theories. And a really natural question, I think, which is suggested by this 0-1 law for metric spaces, is whether the Eurosum sphere is pseudo-finite. So the Eurosum sphere is the per se limit, the continuous per se limit of the class of metric spaces that we're looking at, finite unit interval valued metric spaces. And in previous versions of this project, Isaac and Brad had thought that the almost sure theory of finite metric spaces was actually the theory of the Eurosum sphere, that the almost sure theory agreed with the theory of the per se limit. And that would have answered the question positively that the Eurosum sphere is pseudo-finite. But as we saw, due to this asymptotic result that finite metric spaces don't have any distances less than 1/2 in the limit, this strategy definitely doesn't work. So I want to say that it's analogous to the example of triangle-free graphs, right? The almost sure theory of triangle-free graphs imposes some restriction beyond what the per se limit would give you. In the triangle-free case, we get asymptotically by part tightness, almost surely. In the metric space case, we get asymptotically all distances greater than or equal to 1/2, almost surely. And so as a result, we can't use a 0-1 law argument to prove pseudo-finiteness of the Froissart limit. So in the triangle-free graphs case, the pseudo-finiteness of the Henson graph is a major open problem, and similarly here for metric spaces, the pseudo-finiteness of the Eurosong sphere is open. Okay. And I would suggest that well, I'll say it at the end of the next slide. We'll just do the last slide here. In the classical case, I like to assert this. I say all known, and that means known to me. So I always hope that somebody will give me a counterexample. But all pseudo-finite Froissart limits that I know, and so by Froissart limit here I mean countably categorical. So say Froissart limit in a finite relational language. All known pseudo-finite Froissart limits are simple or NSOP1. NSOP1 is a slight generalization of simplicity. And in contrast, the Eurosong sphere as a continuous theory is SOPN for all n. And that was checked by Gabe Conan and Caroline Terry. And also, even stronger, all known pseudo-finite Froissart limits with trivial algebraicity. So that means they're the Froissart limit of a Froissart class with disjoint amalgamation, true amalgamation, and no non-trivial definable equivalence relations. So this is to rule out some cases like the theory T star IPQ. They all have disjoint 3 amalgamation, all the ones that I know about. And so it follows that their theories are always simple with trivial forking, just like our theory of TAS of metric spaces, generic theory of metric spaces with all distances greater than or equal to 1/2. And by contrast, the Eurosong sphere does have trivial algebraicity and has no non-trivial definable equivalence relations, but it really has non-trivial instances of the triangle inequality, and that's an unavoidable failure of disjoint 3 amalgamation in theory. Sort of just like the unavoidable failure of disjoint 3 amalgamation in triangle-free graphs, which comes from saying we omit a triangle. So it seems like new ideas would be necessary to settle this question, which would also shed light on pseudo-finite Froissart limits in the classical setting, most likely. This is my way of saying that it seems difficult. But it also suggests a picture, that I've been sort of committed to for a while, which is that 0-1 laws for uniform measures often, in a way, try to avoid. It looks like they try to avoid instances of failures of amalgamation. So the finite triangle-free graphs have the failure of 3 amalgamation. You can't amalgamate an edge, an edge, and an edge to form a triangle, and then you get almost surely the triangle-free graphs are bipartite. Well, in a bipartite graph, you have no failures of 3 amalgamation. And similarly here, restricting our distances to be greater than or equal to 1/2 sort of looks like avoiding any non-trivial instances of the triangle inequality. So this is a vague statement. It's hard to know even how to make that into a precise question, but I think it's interesting food for thought. Okay, I'll stop there and see if there are any questions.
Okay, well, thank you very much, Alex. Are there any questions from the audience?
I have a question. Oh,
Sorry, go ahead. You first.
is there a known pseudo-finite Froissart limit that is not the ultra product of some filter on its Froissart class? Is that even possible?
Yeah. So you're asking. This is equivalent to asking about like the finite submodel property, right? Like if you have a case that every sentence in this theory is true of not just some finite structure, but of some structure in the Froissart class, right? Some substructure.
Yeah.
It seems like the sort of thing I should know off the top of my head, but I don't have an example for you of a pseudo-finite Froissart limit that doesn't have the finite submodel property.
Okay.
Certainly there are pseudo-finite structures where that's not true, like a pseudo-finite field of characteristic 0, right, will not embed any actual finite field.
Right.
That's not a Froissart limit. So yeah, it's a good question.
At least in the continuous setting, if you take atomless probability algebras, that axiom that you can cut any setting to something of measure 1/2 will not have compact or finite models, but it's eventually true. Okay, so at least in the continuous setting, you get a positive, let's say you have counterexamples.
Interesting. So counterexamples to you were saying to the question that James just asked, right?
Yes.
Yeah. And so the example you said was just the Adams probability spaces?
Yep.
And that's a continuous per se limit.
Yes, and it also satisfies the 0-1 law.
Okay.
So it is the almost sure limit of the, let's say, probability spaces of n atoms as n goes to infinity.
Perfect. Thank you. Yeah.
But do you not get like approximate satisfaction of that axiom in finite
Well,
like
but
to within some epsilon?
then you're right then, because if basically if you give me an epsilon and you take a, let's say, n large enough such that 1/n is much smaller than epsilon, then modulo that epsilon, the axiom will hold. Yeah, almost surely.
So so doesn't that mean is the Adams probability algebra should be an ultra product of finite?
It is. It is.
It is.
It's,
Okay.
yeah, it is the ultra product of, you just take n, a natural number, you take the interval 0-1, you split it into n pieces, each one of measure 1/n, and you take the ultra product, and it's exactly an atomless measure algebra. So it's extremely explicit. But if you take let's say, if you take the axiom equals to 0, it does not hold in any model. But if you give me an epsilon and you say the axiom holds, let's say the axiom less than epsilon holds, that will be true in a 0-1 way, let's say, eventually. So you do need the epsilon. That's the point. Yeah.
So I guess the conclusion is that the right sort of translation of James's question to not talk about ultra products is to ask, if you have a pseudo-finite per se limit in a continuous setting, is it true that any sentence of the theory will be approximately true in some substructure, finite substructure of it? It seems we don't have a counterexample for that either. Okay.
Yeah.
Okay, I do have a question. Okay, choosing the Lebesgue measure is the natural way of doing things. It's the same thing for, let's say, atomless measure algebras. You do the same trick. You use the let's say, Lebesgue measure, and things work out. But is there like a topological, I don't know, space of types reason or something like this, in which you can show this is the natural one? That has been bothering me for a while. Yeah, and I don't have an answer, so maybe you do. Yeah, like, okay, it's natural to choose Lebesgue, but when you take the counting measure, it's really like, well, you're really taking a sample where every object has the same weight. But when you're choosing Lebesgue, it's just the way you chose things. Is there any reason why that's the way of choosing things? So I don't have an answer, but any insight will make me happy.
Yeah, well, I don't know if I don't know if I know how to answer that question, except, I mean, isn't the question really, is the uniform measure on the unit interval the natural way to pick a random number in the unit interval? I mean,
well, that's why it's a way.
Yeah.
Why the way? Yeah.
Yeah, I mean, it's the way that makes a subinterval of length epsilon have measure epsilon, right? Which is a natural condition. I'm certainly sympathetic to wanting to consider other measures than the uniform one. I think in some cases in the classical setting, there's more natural measures on classes of finite structures than the counting measures. And I'm interested in 0-1 laws for situations when you might have not have a 0-1 law, or maybe sort of the wrong 0-1 law for the uniform measures, but then there's another measure on the class which gives you a better 0-1 law in some sense. I think that sort of behavior can be interesting, and it could be that happens here too. But
Okay, so yeah, that would be the next question. Yeah, other measures will give you different 0-1 limits. Is there anything natural there? Okay, thanks.
I don't know. It's a good thing.
So one idea for a different measure would be, right, every n point metric space embeds into the like the positive unit cube with the L infinity norm on R to the n. And you could think about randomly picking n points in that cube. And then that would be a way of randomly making n-point metric spaces. I don't know if that gives you the same distribution or not. So
It's a good suggestion. Yeah, I don't know. It looks like there's a hand up from Andres, maybe?
Yeah. Okay. On this slide that is now projected, you have something very interesting, and it is the connection between the, the sort of amalgamation that you can have and the behavior of the limit, of the Freisel limit. And this reminds me just another similar situation in continuous logic in a work, joint work with Alex Bernstein and Tapani Huitinen, where somehow we have a construction. It is not pseudo-finite, but it is a Freisel limit, and it falls in NSOP1 and TP2. So it's kind of a weird, combination of bad and good, but it is NSOP1, unlike the Urizen sphere. And the way you show it is NSOP1 is essentially by building three amalgamation of types to be able to, to extract from the three amalgamation of types this characterization due to Artyom Chernikov and Nick Ramsey to prove the NSOP1 for that case. But what's at stake, beyond that result is that there, like here, like in this slide, these two phenomena, the sort of amalgamation of types or small models or something that is allowed is somehow connected with the behavior of the limit. And I have, you say something about the triangle inequality, and also the triangle inequality was responsible for part of our problems in that construction with Alex and Bernstein and Tappan. So can you say more perhaps on this confluence of ideas?
Well, I haven't seen, is that a paper that is available?
Yeah, it's published. Yeah.
Yeah. So I haven't looked at that, but now that you pointed it to me, I will definitely go and read it. It sounds really interesting. It's not surprising, of course, that three amalgamation should come up if you're looking at an NSOP1 structure, because in some sense, NSOP1 is characterized by having some independence theorem, which is a three amalgamation, right?
Yep.
The NSOP1 that as it appears in this slide, where I say all known pseudo-finite Freisel limits are simpler NSOP1, and maybe talking a little bit more about the connection with n-amalgamation, I can just say what my sort of perspective on this or history with this. So in my thesis, I proved a theorem that if you have a Freisel limit with disjoint n-amalgamation for all n, then then it will have a 0-1 law where the almost sure theory agrees with the theory of the Freisel limit. Now, not for the uniform measures, but for some other measures that you pick, where basically you think of the random construction where you sort of build a structure in the class by assigning quantifier 3 1 types, and then 2 types, and then 3 types, and then 4 types, etc. And because you have n amalgamation for all n, you never get stuck, right? And so somehow it seems to me like pseudo-finiteness of Freisel limits in the classical setting can almost always be explained by this sort of construction, right? In the examples that I know, they either have disjoint n amalgamation for all n, or they have some expansion, some finite expansion with disjoint n amalgamation for all n. Now, there's counterexamples to that coming from theories of equivalence relations, but all the counterexamples I know have equivalence relations in them. So you can take the theory of an equivalence class with equivalence relation with infinitely many infinite classes that has no free amalgamation and has no finite expansion with free amalgamation, but it's pseudo-finite, right? But okay, so you can still prove pseudo-finiteness of that theory by sort of limiting the number of classes and sort of filtering your Freisel class by allowing the number of classes to grow. And if you fix the number of classes to be n, then suddenly everything is finite. You can like get around the free amalgamation, okay, and still use the theorem. And somehow this filtering process tends to move you out of simplicity and into NSOP1, it seems to me. Okay, but no further than that. Now, actually, I don't have a theorem that says that. I wish that I did, but that's how sort of, it seems to me that you get these NSOP1 pseudo-finite fair say limits when there's some sort of, you don't quite have actual free amalgamation. You have maybe some equivalence relation, which is blocking it, but you can, okay. Now I peer off and say that's all. I don't know if that addresses what your question was.
Well, I'll have to parse it down a little bit. But yeah, it seems to go in the same direction. Thank you. Yeah.
There's a hand up.
Atticus.
Sorry, this is probably a silly question, but what does disjoint amalgamation look like for metric spaces? What do you take the metric to be between 2 points and 2 different components?
Yeah, so by what is amalgamation, like the amalgamation property for metric spaces?
Yeah. Or in particular disjoint amalgamation. What does that look like for?
Right. So there's a kind of canonical way to amalgamate 2 metric spaces, which is to okay, so you have some metric space A and it has extensions B and C, and you want to define some metric on the union of B and C over A. Okay, so because we're looking at metric spaces with some bounded values, right? So you can't have values greater than 1. You'd like to just say, okay, put the maximum, like freely amalgamate, put the maximum distance between 2 points. Okay, but that might violate the triangle inequality.
Right.
So instead, you put the maximum value that you are allowed to put by the triangle inequality, right? Okay. So the distance from B to C is the maximum over all sums of distances from B to something in A to that C, right?
That makes sense.
And then you have to check that actually works and doesn't introduce any new violations of the triangle inequality, but you can check it.
That makes sense. Thank you.
Of course, in our case of where the metric spaces of interest all have these values greater than or equal to 1/2, there's no problem with the triangle inequality. So you
right. That makes sense. Thank you.
No problem.
Okay, any more questions for Alex? May I ask a couple of questions, but that's just regarding to literature. So you were saying that this theory of the asymptotic, the almost sure theory of the metric spaces is simple, right? Sorry, Utherank 1, you said that?
Yeah, it's simple with, there's no non-trivial forking. So,
but I haven't seen a definition of simplicity in the context of continuous logic. So do you know where can I find that?
Yeah, so there is one. And in fact, our paper gives a reference to a proof of the Kim-Pillay theorem in continuous logic. I'm trying to remember now what that reference is. Probably someone here knows it.
Itai has some stuff about it, but maybe in cats, and you can use it. But now that you ask for it, we don't have really an example of something simple and stable, which is really like metric. Like, for example, this example, the metric plays no role. Yeah, so let's say every point is isolated. So in a sense, there is a theory, but there are no examples. So that's why maybe it hasn't been developed so much, because there's nothing really out there that is really metric, simple, and stable. Yeah, and that's a great question, but you can stare at it for 10 years and not do anything. So it's a hard question.
Yeah, sir.
There was some discussion of that at the end of Kiesler's lecture in this same seminar 2 weeks ago. And it's like Alex Bernstein says, but you do have the Kim-Pillay characterization in your paper, Alex Kruckman.
I'm actually looking for what reference we gave for the Kim-Pillay characterization. So it's actually to the CATS version. So it's to Ben Yakov doing it.
But we worked with Alex Bernstein also on the negative, on the Casanovas Schellach characterization as well. That is, counting partial types.
Right.
You can also do that, and it works for the same class that would, if there were examples, we don't know, but if there were examples that satisfy the Kim-Pillay, then they would also satisfy the Casanovas Schellach counting partial types.
Oh, cool. That's
good. But I think it's just kind of mentioned in our paper, and that's it.
And do you know if
Oh,
You were
go-
mentioning that there were, I mean, non-interesting examples of pseudo-finite continuous structures. Was that correct?
Yeah, so actually it sort of seems like the situation with pseudo-finite continuous structures is a little bit similar to what was just said, which is that there's not so many examples known that are really like
Continuous.
metric structures, right? So you can take the Kiesler randomization of some pseudo-finite classical structure, and you'll get a pseudo-finite structure, right? But that's really taking the classical structure, which is pseudo-finite, and sort of up in a continuous structure. And the atomless probability structure is pseudo-finite, but that's also like, I think that's a Kiesler randomization also, right?
Well, yeah, it's the Kiesler randomization of a 2-point structure, but I mean, it's fairly like, I don't think it's bi-interpretable with a discrete structure
No,
or
it's
anything.
really
Okay.
continuous. I agree
Okay,
with James.
It's omega stable. It doesn't have any strongly minimal sets.
good. Okay, so maybe that's a good example of a really metric.
I was thinking that also, I guess the interval 0, 1 with the order and the usual metric that is pseudo-finite, right? Yeah, that is pseudo-finite.
Yeah, but it's also a compact structure, which is like sort of morally finite in continuous logic.
So the paper by Isaac, the Goldbring-Lopez paper, introduces pseudo-finiteness and also pseudo-compactness, right? That you also might think the proper notion of pseudo-finiteness for continuous structures might be not that you're an ultra product of finite structures, but that you're an ultra product of compact structures, because there's a sense in which compact structures play the role of finite structures in continuous logic. But actually, I think that it's not, maybe someone can correct me if I'm wrong about this, but I think that it's not known whether pseudo-finiteness and pseudo-compactness are actually different.
Really?
Well, for relational structures, they're the same.
Right, relational structures.
Okay.
That's not Lopez. And I think they suggest in that paper, although I haven't asked Isaac about this, that it's not known even if you have function symbols in the language that they're different.
Okay.
So the unit ball in an infinite dimensional Hilbert space is given in that paper as an example of a pseudo-compact structure. And so I guess modulo the conjecture that pseudo-compactness and pseudo-finiteness are the same, you might think that thing should be pseudo-finite as well.
The unit ball of a Hilbert space is bi-interpretable with its purely metric reduct. So well, but that doesn't mean that it actually is like pseudo-finite if you do include the function symbols in the language.
Yeah, so I don't know about that.
Okay. Well, are there any last questions for Alex, perhaps? Well, if not, then let's thank Alex again for the talk and for the replies.
Thank you.
Thank you very much for coming. And so we will have a brief break from the Flotante, and the next talk will be on April 9, and it will be given by Henry Tausner. Okay, so everybody is welcome to come and join, and thank you very much for coming today.
Thank you.
Bye, everybody.
Nice to see you all.
Yeah.
Nice talk. Thanks a lot.
Thanks.
Thanks.
Dario, can you actually add me to the mailing list for the seminar?
Sure.
I
mean, yep, you can.
I mean, I know that it exists now, and I can go and look at the website, but like I might.
Sure.
I'd like to see Henry's talk in 2 weeks.
Yeah, no problem. I think it's very easy because we. Okay, let me just stop the recording, perhaps.